All right. Welcome. Let's get started. A pretty packed lecture today, I feel. At the same time, I'm a little sleepy the past few days, so I think we got to watch the uncomfortable silences. Might lead to undesirable results. And relatively little review this week. Last time we motivated grammatical structure as a tool towards understanding, making for computers to make sense of natural language, of human language, but actually just as much of formal languages. The mechanisms, the basic mechanisms we've introduced already, syntactic structures, and the algorithms we'll introduce today, parsing, apply to programming languages too. The main difference is, or to other formal languages like the language of arithmetic expressions that I used as an example, the main difference is that natural language is typically ambiguous. There will be more than one candidate interpretation, and we've already seen some examples. We formalized this notion of grammatical structure by introducing context-free grammars. That's the one piece I'll quickly review today. Then we introduced training data, sources of knowledge about hand-coded knowledge about grammatical structure. And with training data, we then generalized the formal model, the notion of context-free grammars to probabilistic context-free grammars. What we have not done yet is actually take these to use. We've only poured the concrete. We've built a foundation. Today we'll start building on that foundation. But before we do so, I'll briefly talk about parser evaluation. I've moved that to the top here because that's the most important missing piece you need for the current assignment. And then I'll talk at length about syntactic parsing and derive a framework called generalized chart parsing, and that's where we'll pick up again next week and look at how we can put an adaptation of the Viterbi algorithm actually on top of the data structures, the syntactic trees produced by this framework. So that's the outline. Here's the one thing I wanted to go over just one more time. A CFG is a 4-tuple C sigma PS, where we assume that there's some set of abstract categories, things we cannot observe. S for sentence, NP for noun phrase, VP for verb phrase, but also the categories, the lexical categories, the morphosyntactic word classes that we assign to individual words, as we have done in part of speech tagging, they come into this set of categories. And then sigma is the vocabulary, the actual observable units, actual language, the words. And we'll often call the categories the non-terminals and the words the terminals. And the rules that allow us to put things together, that essentially spell out the grammar of the language, take the form of these category rewrite rules, productions, where I have a category, a non-terminal symbol on the left-hand side, and then some sequence of non-terminal or terminal sequences on the right-hand side, separated by this arrow indicating that I can rewrite an S as the sequence NPVP. Or we'll sometimes look at them in the reverse action. When we have the sequence NPVP, we can group those. We can introduce a new constituent, as we called it, and call that constituent of category S. And we had briefly, and the fourth element is that we need some notion of which types of constituents, which categories signify complete utterances, things that I actually accept as part of the language. So that's the start symbol. And then we had briefly observed that in general context-free grammars, we want it to be the case that the left-hand side of each production rule is one symbol alpha that comes from the categories. So on the left-hand side, I can only have a non-terminal symbol. I would like to think that makes intuitive sense, because the words, the terminals, they are not the names I can use to group, to name groups. That's the categories. And on the right-hand side, in this general form, we say we can have any non-empty sequence of beta 1 to beta n, and these can be non-terminals or terminals. So all beta I are members of the union of C with sigma. That's the grammar formalism. Unless you have any questions on that. In the current assignment, the first part, we make you read out a large context-free grammar from the Pentree Bank. Then let's talk about, once we've built a parser towards the end of today's lecture, how would we evaluate it? And as with classification or sequence labeling, one very important property of success is going to be how well does it solve the problem? How accurate are the hypotheses, the analyses produced by the parser? So the parser takes a string and returns a tree, and we'll want to judge the quality of the tree. We have some idea of what the right tree is. For our purposes, that's the tree that the linguistics graduate students at the University of Pennsylvania put into the Pentree Bank. That's the ground truth. That's the gold standard. Our parser, given the same string, will not necessarily give us the same tree. It would be great if it did, but at times it won't. And so we need some way of comparing trees. And one obvious way of comparing trees, so now we're evaluating at the level of structure. It's not something we have done before. In tagging, we evaluated the tag accuracy, the average correctness, if you will, of the individual tags. Now we want to know what is the correctness of the tree. One obvious measure would be, how can we compare trees? We can just ask. Sorry? Probabilities. We have two trees. I want to compare them. I'm not sure I follow yet. I think you're a little further afield than I'm asking here. So much more down to earth. We have two trees. One gold standard, one from our parser. We want to ask, is this the correct tree? An obvious measure would be to say, is it the exact same tree? Does it have all the same nodes with all the same labels and daughter sequences? Are these trees isomorphic? Do they have the exact same structure and labels? That would be a very strict measure of success, because the average sentence length in the Pentree Bank is 20 words. This is newspaper text, long sentences. It will be very easy to get some small aspect of the structure wrong in some part of the sentence and yet have everything else right. If we compared the tree at large, the entire tree, and said you get a point when you have the exact same tree and otherwise you get 0 points, we would not be doing justice to parts of the structure that may be right and penalize very heavily. Let's say there was one minor error somewhere. That would be just as bad, a tree that is pretty good, but has one minor wrong label. That would be just as bad as a tree that is completely random. And that's a harshness in evaluation that we don't want. We want something more granular. We want something that tells us degrees of correctness. You had a question? Yeah, you're up to something. So the closer to the leaves, the smaller the error, the less important. You have this intuition that if the error is in a smaller subtree, yeah. So if it's just the category of one word, that's less important than the label of a large constituent. Yeah, I think that's a healthy intuition, and what we'll do actually captures part of that. So what we need is some way of comparing trees in a granular, in a graded manner. Tree similarity, not just right or wrong, but tree overlap, if you will. And we'll derive that by breaking the tree down into its pieces, and the pieces are the individual constituents. And then we'll say a tree is essentially a set of constituents, and we'll ask how similar are the two sets, how much do they overlap. And that's a measure called Parser, originally proposed by Black et al. In '91. And the two variants, labeled and unlabeled, these are also fairly common in much evaluation of machine learning, where what we're doing here is called structured prediction. Parsing, statistical parsing, is given a string, find me a structure that represents the analysis of this string. In our case, the structures are trees, and they're labeled at the nodes. And we could ask, do we have the right structure, no matter the labels? That could be very useful already, because then we have all of the grouping. Because the structure of the tree tells us how things lump together, what the constituents are. But of course, it's even better to have the right tree, the structure, plus knowledge that this node is a VP, this node is a sentence, this node is an NP. So that's the labeling. So we can compare the trees, our constituent trees, just in terms of the structure, the shape, or also in terms of the labeling in addition to that. And we'll now look at the labeled variant. That's the most commonly used one, and that's what we ask you to implement. So there's a tool called evalb, but of course we'll, to understand how this actually works, implement our own variant. So here is the problem, a gold standard tree and a tree proposed by our parser. The sentence is a pretty big dog's house. It's actually not a sentence, it's a noun phrase. It's no verb. But still it's a perfectly legitimate utterance of English. What did you see the other day? Question mark. A pretty big dog's house. Showing the trees here in the S expression, the Penn treebank notation. Do you see the difference? If you try to sort of visualize these two structures. The indentation, I mean, they clearly look different. Pretty is an adverb, big is an adjective, JJ means adjective, dog is a noun. Apostrophe S is the possessive marker, house is a noun, is a determiner. So the parts of speech are the same in both of them. But the grouping is different. Can you see the difference? In fact, I lied to you. There's one difference in parts of speech. So this pretty is an adverb. This pretty is an adjective. Yes?
Well, the pretty and big are different. And on the system output, the nom JJ kind of encompasses everything that's under it, while on the other side, it doesn't. So you have like taller branch.
Yes. Yes. So let's apply that to what we see. The grouping tells us how things hang together, and hence also how we are to understand them. So here we have, so nom means part of a noun phrase in the Penn treebank syntax. So here we have dog's house. That's one group. That just means house owned or somehow possessed by a dog. And we have that here too. So in both cases we're talking about a dog's house. Then here we have pretty and big hanging together. and pretty actually has a different part of speech here. So that's the adverb pretty as in fairly, or to some degree, or quite. So this is pretty big, whereas here we have big dog's house, which is pretty. So the difference is in how the pretty is interpreted, and in one case it modifies the bigness. It's a fairly big dog's house, and we don't know whether the dog's house is pretty or not, what it looks like. In this case, the pretty actually is part of the noun phrase. It's a sister to the big dog's house, so the dog's house is both big and pretty. Different interpretations driven by different structures. Okay, so these are the two different trees, both reasonable. I mean, without seeing the house, without knowing the story, there's no knowing for us. So how do we compare? How do we derive? So what's the goodness of this tree is what we're asking. How good is this tree? It's not terrible. It has dog's house, it has big dog's house, all of that, all of those relations are present in both analysis. Just the pretty receives a different role. So there's one error in the parser output here. And how are we going to derive quantitatively that notion so that we can evaluate? We'll break this tree into its constituents, and we'll count essentially string positions by tokens, starting from 0 to the last word. So I might as well write the string on the board here. So the apostrophe S is a token of its own right. And if I now write the indices between the words, so what we count here are essentially the spaces or the token boundaries. And then from 0 to 6 is the entire string. And there is a constituent here at the top that says for the entire string, there is in the gold standard a constituent labeled NP. And for the substring that goes from 0 to 1, that's the token there is a constituent labeled DT, and so on. From 1 to 3, that's pretty big. We can actually trace the brackets here. And so on. So what we do here is we break this tree into, we break it down into a set of what are often called labeled bracketings. A constituent is a bracketing, it groups, and the span of the brackets we actually capture in terms of substring indices. And then we do the same thing for the system output, and we should see the difference regarding pretty. So first of all, pretty is at position 1 to 2. Here it's an RB. Here it's a JJ, adverb versus adjective. In fact, I think, no, yeah, in a sense, there's color coding coming up. And furthermore, we see that the different tree structure manifests at here, 1, 2, 3. We don't have this adverbial phrase in the parser output. And what we have in addition here is one more nom grouping big dog's house in addition to dog's house here. So what we've color-coded in red here now are is the intersection of these two sets of labeled bracketings. So the labeled bracketings that both trees have, and hence in the system output, the red ones are the ones that are correct. And the black ones in the gold standard are missing over here, and the black ones in the system output are not motivated. They're spurious. So we're missing some and we have some extra, essentially. And that we can translate into notions that we actually already know, false positives and false negatives. And we can derive the same definitions of recall and precision. Recall is how many of the gold predictions did we actually obtain, correct over gold. Precision is what proportion of the actual system outputs were correct. And again, we can compute F-score as the harmonic mean, which in this case gives us 7/9. So that's an application, an adaptation of metrics that we've used repeatedly, recall and precision. They come from information retrieval originally, and F-score to combine both into one single number. We do that for the sole purpose of having one number to compare. So you tell me my parser has 91 points F-score, and I say, hey, I have 91.5. That's easy to compare. If you say I have 89.5 recall and 93.2 precision, that's harder to compare. So we do this F-score mean computation just to have a single number to compare. These are actually, in a sense, more meaningful to interpret. Okay, so that's the parser eval metric. That's how we will address this problem of determining the degree of correctness of a tree. Any questions? No. Time to move on then. Right. But there are two variants of parser eval, and in our first calculation here, we considered all of the non-terminals. But some of the non-terminals, notably the pre-terminals, those that dominate a terminal, are parts of speech. So one could argue they are actually part of a different problem, a problem we have solved already, part of speech tagging. And if we're doing syntax, then let's not evaluate again the quality of the parts of speech, but let's focus only on the tree above the preterminals. So let's ignore the preterminals, and that's what we're doing here. So grayed out, we have all of the parts of speech. That's effectively the sub-problem of tagging. And now we only evaluate in terms of the remaining nodes. We ignore the preterminals. And then we get smaller numbers, of course, but it's again the case that recall and precision have the same value, and hence F-score is the same 2/3. That's the variant of parser eval we'll ask you to implement. And essentially it means exploding, as I sometimes call it, a tree into a set of these triples. These can be lists, 3 elements. Ignoring the preterminals, so kind of stopping as you traverse the tree soon enough to not output a triple for DTA or RB pretty. And then you have the two sets, and then you can do set intersection and compute correct and gold and system those cardinalities. All right. That was almost giving away the... Well, you still have to code it. And now, finally, let's actually move to algorithms that compute syntactic structure. And that's, in a sense, if you will, moving to a procedural view. So before we do that, here is the problem definition to remind us. We have a context-free grammar. I'm only showing the set of productions here. But the non-terminals and terminals are clear by convention. Non-terminals are all caps. Terminals are lowercase. And the start symbol by convention, I assume, is S. So this is a full context-free grammar if you accept these additional conventions. And let's assume we analyze the sentence Kimmedore's snow in Oslo. Here is a parse tree. Looks very similar actually to a parse tree for Spanish that we saw last week. It's the same structure. And now we can formally say that a valid parse tree given a grammar and a string, that is a complete derivation, as we'll call it, because remember we said that to be a member of the language we derive the string from the start symbol. We successively rewrite. That was the definition of what the strings of the grammar, what that set actually is. And so we'll say all complete valid derivations are rooted in the start symbol. Obviously they have to be of the right category. They label their internal nodes with categories from C and their leaf nodes with words from sigma, and each internal subtree of or local subtree of depth 1 instantiates one of the grammar rules. So for each of these subtrees here I can go to the grammar and say, okay, I can have a subtree that says a VP dominates the sequence VP PP because I have this rule here. VP goes to, I maybe failed to explain to you this shorthand notation. So in the grammar here, in this compact representation of my context-free grammar, I'm using this vertical bar, the pipe symbol, as a disjunction, an alternation. You've seen that in extended Bacchus-Nauer form. This means there are effectively 3 VP productions. VP goes to V, or VP goes to VNP, or VP goes to VPPP. And hence I have one rule, VP goes to VPPP, that licenses this subtree. So that's formally the parsing problem. Compute all complete derivations that satisfy this definition. Do we have those? Is this a valid complete derivation? It's rooted in the start symbol. All of the internal nodes have category labels. The leaves have non-terminal word labels. And if we sort of check off each of the subtrees, there is a corresponding rule for all of them. So this is a valid complete derivation. Do we have all of them? Some of you nodded. It's going to be hard to prove that wrong, but I mean, there's an awful lot of white space here. There would be room for another tree. So let's see whether maybe we can find another tree. The other. So you think there may be another one, but you wouldn't know what it would look like? Yeah. It's our canonical example. You'll get tired of this example. So it's I saw an astronomer with a telescope. The police chased robbers in a stolen car. I ate sushi with tuna or with chopsticks. So-called PP attachment ambiguities. So which interpretation do we have here in this tree? Exactly. It's whether Kim or the adoration is in Oslo. Whether the snow is in Oslo or the adoration is in Oslo. It appears to be the case that whoever does the adoring is in the same place where the adoration happens. And which interpretation do we have here? What is in Oslo? That was a couple of weeks ago. The snow had not come to Oslo, so Kim was in Oslo. He was doing some adoring of snow in the mountains, waiting for the snow to come to Oslo. But whenever you see these prepositional phrase modifiers, expect ambiguity. This sentence certainly can also mean that Kim actually was away from Oslo last weekend when the snow arrived and was sent pictures, and from where she was in Spain adored the snow that was in Oslo. How do we get this? Where's the rule that gives us this additional tree? What's the important rule that we use here and not here? It's this one. So we have a PP in Oslo, and the PP is what we call a modifier. It can combine with either an NP and give us just a larger NP. NP goes to NP followed by PP, or it can combine with a VP. VP followed by PP can be a VP. That's where we get the ambiguity. So PP modifiers are prepared to modify nouny things or verbal things. And because we have this rule here, this is another complete derivation. It satisfies all of these conditions. So the parsing problem for natural languages is to compute this set. All derivations, all trees that satisfy these conditions. That's the problem we'll now start to solve. And it's actually a hard problem. We'll very briefly introduce a naive algorithm. That's what you often use in compiler technologies, the so-called recursive descent algorithm. It's about the most straightforward parsing algorithm I can imagine. And it's so-called top-down or goal-oriented. It assumes that we're looking for a specific category. Initially, that will be the start symbol. We have a string, and we have the expectation to prove that this is a sentence. So we say, we're looking for an S. And now we'll use all of the grammar rules that have S as their left-hand side, that rewrite S. And we try to build trees. So we go to the grammar and say, which rules have S as their left-hand side? There's only one. Okay, then that gives me a new parsing problem. I need to find a sequence of an NP followed by a VP. So that's where we recurse. So we pick that rule, that grammar rule, and now recurse and say our next parsing goal is NP. And should we succeed in that recursion, then we're not done, then we still need to pursue the parsing goal VP. When that succeeds, we're actually done. We have found an S. So that's already sounding like a recursive algorithm. So what we'll do is we'll successively instantiate the right-hand sides of each rule that has the current parsing goal as the left-hand side. There was only one. S goes to NP-VP. So we'll successively instantiate the NP and the VP sequence of the right-hand side. Instantiate the right-hand side means change our parsing goal in recursive calls. So our parsing goals in the recursive calls become each of the beta I from the right-hand side. And when we can do that for all of the elements of the right-hand side, the entire sequence, then we have succeeded and returned successfully to the next higher level. This is a recursive process that builds trees from the start symbol, and the trees will just be increasingly large. So we need a termination condition, and the termination condition, of course, needs to be in regards to the string, the input that we're actually trying to parse. We haven't talked about that yet. So the recursive calls terminate when our current parsing goal is a prefix of the string that we're trying to parse. So how do pieces of the string actually become parsing goals? Well, at some point we get to these rules that we call lexical rules, where the right-hand side actually contains non-terminal symbols. Terminal symbols, words. And we still recurse. So we say we're looking for an NP, Commodore Snow in Oslo, so first level of recursion. Our parsing goal is NP. We say which rules have NP. There's on the left-hand side, there's several. One of them says NP goes to Kim. That means there will be one recursive call where our parsing goal alpha becomes Kim. We compare that to our input string, and that gives a match. And so we have successfully parsed part of the input string, and that recursion returns to the caller. So that's a very simple algorithm. I'll skip how it actually passes up information. It needs to pass up two pieces of information, a partial tree and how much of the input string it has actually found, where that prefix ends. And if you want to play with it, here's the code. So this is the complete recursive descent parser in Lisp. And that's, I think, about the shortest parsing algorithm I can imagine writing. But this is just to get you started thinking about how could one go about solving that problem. It's not the algorithm that where we will put our money. It has severe drawbacks. But it's certainly good enough for non-ambiguous formal languages. Has its applications. So should you ever have to parse a non-ambiguous formal language, that would actually be a decent candidate. So let's talk about the complexity of the parsing task. I said it's a difficult problem. Let me convince you of that. So here I'm assuming that I have sentences with n prepositional phrases. So I write it as Commodore Snow in Oslo in the nth. In more realistic examples, that would maybe be Commodore Snow in Oslo on the hill behind the lake in the forest on Tuesday at 3 o'clock with Sandy and so on. So that's the strings we imagine for the growth in ambiguity and hence the complexity of the parsing problem. All that matters is that we have n prepositional phrases, no matter what they are. So we can assume the silly sentence Commodore Snow in Oslo, in Oslo, in Oslo. And here I've written down how many complete results there are for a given n. Commodore Snow has only one interpretation. It's not ambiguous. But we already know that Commodore Snow in Oslo has two interpretations, one prepositional phrase. If I add another prepositional phrase, I end up with 5 interpretations. And we used to ask people to write down those 5 trees in an exam. It's possible, but it actually takes a lot of time. I would encourage you to maybe try doing that at home. We'll not ask you that question in the exam, most likely. I mean, I can't promise, really. But it would be an incredibly good exercise if you tried to identify all 5 trees that you can build for a string like Commodore Snow in Oslo, using that grammar on the preceding slide. And why is it not 4 or 6? If I add another prepositional phrase, I jump to 14. With only 4 prepositional phrases, I'm at 42 already. That's not looking good, or at least that's very impressive growth rate. That's the so-called Catalan series, the Catalan numbers. It's an exponential series. Exponential is bad. So here I've plotted that in terms of the number of recursive calls inside of the recursive descent parser. Essentially, how often does it need to pursue a new parsing goal? And this is a terrifying curve. So that tells us something about the complexity of the parsing task, and it looks really bad because this is the number of results it's expected to compute. So with only 8 prepositional phrases, so 8 times 3, that's 24 words, plus Commodore Snow, 27 words. A comparatively short sentence. In newspaper, we find sentences up to 50 words, like 60. The sky's the limit. We can already have close to 5,000 different results. So the ambiguity grows quickly, and it grows exponentially. And for our current definition of the parsing task, enumerating all complete derivations, what's going to be the complexity of any algorithm that solves that problem? It's an exponential problem. it's asking to compute and return an exponential number of results, it's going to be linear. Please don't nod. No, there's no way to compute an exponential number of results in less than exponential time. Because even if computing one result took me no more than one operation, there would be an exponential number of operations, because the number of results, the number of solutions grows exponentially. That's really bad. So even for fairly simple constrained formalism like context-free grammars, which linguists don't accept as linguistically adequate, the parsing problem already is really bad. The complexity grows exponential. And we'll have to cope with that. And we'll apply a clever trick. So it's not hopeless. Don't give up on that problem yet. But before we do so, let's reflect just a little on the space of possible approaches we could take. And we'll break them down into top-down versus bottom-up approaches. And that's terminology that sounds familiar to you, of course. But what does it mean in terms of parsing natural language using a formal grammar, a context-free grammar? The recursive descent parser that I briefly sketched, just like the definition for what are the strings defined by a grammar, what is the language of a grammar I gave last week, is an instance of this top-down perspective, where you say, okay, I have a string, and I know to successfully parse it, it needs to be an S. And I have these two things to connect. A start symbol up here, a string down there. And now I somehow need to put a tree in between that satisfies those formal constraints, where all of the subtrees instantiate a rule of the grammar, all of the internal nodes are labeled with categories, and the leaf nodes actually are the tokens of the string. In a top-down approach, I do what the recursive descent parser does. I build the tree from the root towards the string. And in the contrasting bottom-up approach, I start with a string and say, how can I group things? Kim adored. I have a rule that has Kim as its right-hand side, so I can assign the category NP to Kim. I have a rule that has adored as its right-hand side. I can assign the category V to adored. And then I could ask, do I have a rule that allows me to group NP followed by V? What would be the constituent category for that grouping in a bottom-up parser? You're right to be quiet. There is no such rule. Kim adored is not a constituent. Snow is an NP. Adored snow, V followed by NP. Can I group that? Yes. I have a rule that says V followed by NP. You can group that as VP. So that would be bottom up. I start from the string and try to apply the rules, looking at their right-hand sides. And whenever I can match a right-hand side to a subsequence that I have derived already, I group them, I introduce a new constituent. So that's top-down, goal-oriented versus bottom-up, data-oriented parsing. Connecting the start symbol and the string, putting the tree in between, either working from the top towards the string or working from the bottom upwards from the string towards the start symbol. So in this respect, top-down and bottom-up really are easy to interpret. If you think the bottom is the string and the top is the root. And in the recursive descent parser, a rule like this one that is actually from our grammar, it's called a left recursive rule because the left-hand side category also occurs in the right-hand side, and specifically as the first element of the right-hand side. So recall the recursive descent parser will say, I need a VP. Give me rules that derive VP, and I'll look for their right-hand sides. It will find this rule and will say, okay, I'll go looking for a VP. And it will continue doing that. So that gives us infinite recursion, and hence left recursive rules I cannot parse, or I could not have in my grammar using a recursive descent parser. Slightly more abstract, in pure top-down parsing, the search is actually uninformed by the string until the very end. It's only the termination condition that says, have I coincidentally found a prefix of the string? It's trying to build whatever trees it can derive top-down. And mainly for this reason, bottom-up parsing is a predominant paradigm, I think we can say, in natural language parsing, where there is so much ambiguity. There are hybrid strategies, of course, mixing top-down and bottom-up elements, but it's very important to consider what the string tells us early. And so this bottom-up bias is pretty strong in natural language parsing, and it's what we'll assume for the remainder of the course. However, it's not that bottom-up parsing is free of any termination problems. Imagine I'd add a rule to my grammar, as linguists sometimes like to do, that says NP goes to NP. You're well-educated computer scientists, you would say, why would you ever do that? An NP is an NP is an NP. I'm not really deriving any new knowledge doing that. But in formal syntax, people might want sort of this extra note. There's something going on here, and it doesn't change the category, but still it changes something. So that would be problematic. We need to rule that out. And strictly speaking, a similar observation, a similar criticism can be made for bottom-up parsing, because we start from the string, we group, and only towards the end, when we have tried grouping over the entire string, will we ask, have we actually found one or more trees that are rooted in the start symbol? So we only consider the start symbol very late in the process. I mean, we have to connect the two universes. But this is actually often a feature, because it means that even if I fail to find a tree that is rooted in the start symbol, I still have partial analyses, and these may actually be useful. For example, in a grammar checker, where maybe the whole thing is actually not grammatical, but the intermediate trees that I can build for substrings may still be the building blocks for the grammar checker to give feedback to the user. Yes? Yes? So you're asking what happens with rules in bottom-up parsing, I assume? I mean, in top-down parsing, you would just work faithfully through all elements of the right-hand side, one by one. Call yourself recursively, go on to the next. In bottom-up parsing, when we sort of look at possible sequences over the actual string that we can match against right-hand sides, we can apply that to arbitrary length sequences. That's what we would have to do. But of course, we can index that. We can say, okay, a rule that starts, well, it's too far back. The matching needs to find the first symbol. When it fails finding that, there's no point searching further of the right-hand side. So that's actually not a terrible matching problem. Okay, so that was the high-level reflections. We'll introduce more sophisticated algorithms than recursive descent after the break. Before we take that break, Anton has an announcement that he would like to make.
Yeah. So I come from the career contact in Canada, and so some of you might have heard about Startup Lab before. It's like an incubator with about 70 businesses.
Time to resume. So that was all fairly high level. unless any of you came up with high-level questions regarding this top-down versus bottom-up perspective, I'm inclined to move on. We'll be doing bottom-up parsing for the rest of the semester for the given reasons. And before we do that, this is the most important 15 minutes of your master studies at the Department of Informatics. Certainly, from my point of view, the most important 15 minutes of this class. I mean, Mohav may or may not agree with that. This is an important insight I want you to take home, is what I'm trying to say. So I've repeatedly said natural language is highly ambiguous, and we've observed how with prepositional phrases there's this exponential growth. And in fact, you might think, who puts 5 prepositional phrases into a single sentence? It's not only prepositional phrases. There's another very common construction that has the exact same behavior. That's the one that Mohav studies in his doctoral dissertation. Compounding in English is done in the syntax. Towel, rack is 2 words, but they group into, in Norwegian that would be one. I mean, you do the compounding in the morphology, in the word formation. English does it in the syntax. Paper towel rack, what's that mean? A towel rack for paper. That's certainly, I can parse that one, a rack for paper towels, or a rack for towels made of paper. You can build a rack from paper, you fold it neatly, and then small towels can go on there. A gold or an iron towel rack, that clearly brings out the other interpretation, where the towel rack is made of iron. So the ambiguity is whether I bracket paper towel before I bracket it with rack, or whether I bracket towel rack before I combine it with whatever that third element is. And you know, regions. So compounding with more than 3 elements, you love doing that, as do we Germans. And so kitchen paper towel rack sales person course. I didn't count, but I think that gets us into the 4,000 range, because the growth of ambiguity is exactly the same in English compounding. It's the Catalan series, as there is with prepositional phrase modifiers. But the poster child example in natural language processing are the prepositional phrases, the astronomers with telescopes, and so here I throw out another one, boys with hats from France. What do you think that means? Isn't that obvious? The boys, so they're French boys, and they have Norwegian hats, or whatever. We don't know where the hats come from, but they could also be Norwegian boys with French hats. So the hats could be from France, or the boys could be from France. So we see an ambiguity here. And here I've drawn the space of syntactic analyses in a new format. It's sometimes called the ballistic format, because you can kind of think of arrows pointing, shooting. And I'm using the same counting scheme I had before. So I'm counting the inter-word spaces. And I'm starting from 2, just alluding to the possibility of embedding this whole thing in a larger sentence. Kim adores boys with hats from France. She surely does. And what I've indicated here are all of the groupings, in a sense the labeled bracketings that we would obtain in the Parseval set. And up here I have spelled out the categories. There are only 2 categories, NP and PP. Well, there are also prepositions here, of course, but I don't bother putting the label into the legend here. So I only care about the NP and the PP bracketings. And I say that 1, 2, 3 are all NPs. That's sensible. And so are 6, 7, and 9. So 6 is boys with hats. Yeah, boys with hats are boys. That's an NP. And hats from France. That's an NP. And 9, the whole thing, boys with hats from France. That's an NP. You can hopefully agree to those category assignments. And now I have 3 PPs, 4, 5, and 8, with hats from France and with hats from France. With hats from France is a prepositional phrase. It's about being, well, having hats. And presumably the from France then is inside of the noun phrase, inside of that prepositional phrase. So that's just another way of drawing. We know there are 2 trees, but I draw them into a single graph. That's the trick I'm applying here. That's what I'm trying to do. And up here, this edge, as we'll call it, or arc, now represents 9 and NP, so the whole thing is an NP. But I observe that given the rules of the grammar, there are actually 2 ways of calling that substring an NP. And I can call that an NP by virtue of combining 1 with 8, boys with hats from France, or by virtue of combining 6 with 5, boys with hats from France. In both cases, I take one NP, 1 or 6, and combine it with 1 PP. And I derive a new NP. So I'm using the rule from the grammar that says an NP followed by a PP I can group as a larger NP. NP goes to NP, PP. That's the rule I'm using here. And in this graph, there are actually 2 possibilities of using that rule. And both tell me that from 2 to 7, edge number 9 here, will have the category NP. And that's what we will call local ambiguity. The ambiguity is local to this substring. For the larger sentence, Kim adores boys with hats from France, all I need to know is that what follows adores is an NP. I don't need to know whether the hats are French or the boys are French. All I need to know is that the syntactic category of that part of the string can be NP. And that knowledge is enough to say, okay, the whole thing can be a sentence, because adores boys with hats from France, we're going to call that a VP. It's a verb followed by an NP. And Kim adores boys with hats from France, we'll call that a sentence, because Kim is an NP followed by a VP. So this ambiguity is local to this part of the sentence, 2 to 7. It can remain within this NP. And we'll define local ambiguity as a substring where there's more than one way of arriving at the same category assignment for that substring, or deriving the same category assignment. So if I were to ask my parser to give me all complete trees, it would return 2 trees. But both trees would say this string is an NP. And I can keep it at that and say I make a note of there being 2 trees, or 2, well, not 2 trees actually. I make a note of there being 2 alternate ways of calling this substring an NP, but I record that fact only once. I put only one such edge here into my graph and say edge number 9 represents the finding that this whole substring can be analyzed as an NP. And that's all I need to know to parse a larger sentence. And now if you imagine girls with sweaters from Finland adore boys with hats from France. How many readings are there going to be? Some. So girls with sweaters from Finland, is that ambiguous? Yeah. Finnish sweaters, Finnish girls, so that's 2. The boys with hats from France, that's another 2. These will at least cross multiply. Finnish girls, French boys, Finnish hats, French boys, Finnish girls, French hats, Finnish hats, French hats. No, Finnish sweaters, I'm sorry. So there will be at least 4 readings. But all of them are sentences. They will all have the same top level category. And they will all call the first part an NP, girls with sweaters from Finland, I guess. And they will all call the final part an NP, boys with hats from France. So the trick, the key insight here is that ambiguity that arises for some substring can be kept local to that substring. I don't need to cross-multiply that to determine whether that whole whether that whole string can be analyzed as a sentence. I don't need to take into consideration all the different ways of calling this substring an NP when trying to ask whether the larger string is a sentence. That's what we accomplish here by putting only one edge into this graph from 2 to 7 and recording that, yes, 9 tells me 2 to 7 can be an NP. I've done the grouping. You can imagine I do this bottom up, looking up the rules of the grammar. And effectively, this graph represents 2 trees. The 2 different, internally different structural analyses that both tell me this is an NP. And for that reason, it's called a forest. So this is a fundamental data structure in parsing natural language, a parse forest, where a single item, this edge number 9 here, actually represents 2 different trees. And that key insight is what we'll exploit next in writing an algorithm that parses using context-free grammars in polynomial time, even though we observe the problem is exponential. That's a miracle. We'll reflect a little more on that. Let's first look at the algorithm. So it's called the Koch-Kasami-Younger algorithm. These 3 gentlemen discovered the key insight pretty much at the same time, late 1960s, and it was a breakthrough for natural language parsing. So the basic data structure is a matrix that represents exactly the same information as this graph. So if you tilt this matrix 45 degrees, you can probably even see how, well, what the correspondences are. So the counting is the same. This is a different sentence now. We're back to Kim adored snow in Oslo. The counting is the same, and each cell in the matrix represents a grouping for one substring. And the substring is determined by the row and column indices. So the row index is the start into the string, and the column is the end into the string. So what's the string that this cell 0 to 3 represents? Which substring is that? Kim adored snow, thank you. And that is actually a sentence. So this cell represents all of the bracketings, all the constituents I can find for the substring that starts at 0 and ends at 3. 0, 1, 2, 3. 3 is behind snow. Correspondingly, this cell, the top right cell in the matrix, will represent the entire string. It goes from 0, the start of the sentence, to, in this case, 5, the last word. These cells, what do they represent? The lower diagonal. Single words. So 0 to 1, NP, that's Kim. 1 to 2, V, that's adored, and so on. And in fact, as we move upwards in this matrix, the length of the substring that each cell represents or analyzes grows monotonically. So the second diagonal here, these are strings, substrings of length 2, 0 to 2, Kim adored. That's actually not a constituent. We don't have a rule in our grammar that combines NP followed by V. 1 to 3, that's adored snow. V followed by NP gives a VP. So we get the same, if you kind of compare these side by side, it's the exact same information. I find this easier to read. Our algorithm finds this much easier to, to process. So that's how we'll represent essentially the constituents that we find. And that's what the CKY algorithm computes in a relatively straightforward manner. It fills in this matrix in a bottom-up fashion. It has one initialization step where it goes through the input, the string, so I from 0 to the length of the input, and then looked up over here all rules from the productions that have input at index I as their right-hand side. So input at I, input sub I, that will be Kim, adored, snow, and so on. And so here we're looking up all rules. Alpha goes to one word of the input at position I. For each such rule, we take the left-hand side, the alpha, and put it into chart cell I at position I plus 1. So for I equals 0, that will be this chart cell. Input sub I will be Kim. We'll look into the grammar. It will give us one rule. NP goes to Kim. We'll put NP into this cell. That's the initialization. We effectively use the lexical rules of the grammar and fill the lower diagonal, find the categories, the parts of speech, if you will. So in these toy grammars, I actually don't have parts of speech. Kim is an NP directly. Question? No, you haven't missed it yet. We're not there yet. That would be a problem, you're saying. Yes. We'll come back to that. So now we have looked up essentially categories for the words. Now the actual grouping can start. And the grouping here has 3 nested loops, L, Y, and J, which all by and large range between 0 or 1, the start of the string, and the length of the input. And they now say, here in the body of this nested loop, I will try to combine 2 cells from the matrix. The matrix is called a chart. The combination of I to I plus j and I plus j to I plus L plus 1, that designates 2 cells from the table. And so in the body of this innermost loop, I'm asking, can I find beta 1 in this cell and beta 2 in this cell? And is there a rule, alpha goes to beta 1 followed by beta 2 in P in the grammar? And if so, then I have found a new grouping. So I'm matching sequences of categories from the cells against the right-hand side of rules from the grammar. This is a very abstract notation here, but and whenever I find a rule that groups beta 1 and beta 2 from the 2 cells that I'm currently considering for grouping, then I add to my chart, namely to the cell I to I plus L plus 1, the left-hand side of that rule. So I add alpha into that cell. So for example, at some point I might be looking at this cell 1 to 2, and that would be, so I is 1, J is 1. That would give me 1 to 2 here. L is also 1, so I plus j is 2. I plus L plus 1 is 3. So I'm looking at these two cells at the current innermost iteration step. Now I'm asking for beta 1 from this cell, V, and beta 2 from this cell, NP. Is there a rule in the grammar that has V followed by NP as its right-hand side? Yes. That's the rule. VP goes to VNP. Hence, alpha, the left-hand side of that rule, over there, now is adjoined into this cell, namely the cell from I1 to I plus L plus 1. And effectively what I have done here is I have computed a new constituent. I've computed a new grouping. Because now I've discovered that from 1 to 3, adored snow, I can call that a VP. And the 3 nested loops just make sure that the parser makes one pass filling in diagonals in the cell for substrings of increasing length. So initially L is the length, and we, well, L plus 1 is the length of each cell that we're currently computing. And so we start with the smaller substrings and compute increasingly larger substrings. Of course, we need to make sure that we only combine from cells that are actually next to each other, that are what we call adjacent. And how do we determine that? Which cells in the table actually correspond to adjacency in the string? Any ideas? The diagonals. Well, I'm asking, how do we know that for a pair of cells, whether or not they are next to each other, so that it actually makes sense to try and combine them? One down or one to the left. So that was certainly the case here. So this VP combines these two cells. Yeah, but let's say this S here, or even this S here, from 0 to 3. Which combinations of cells can I put together? No, I don't skip them. I need to evaluate, I need to try all combinations. But when the cell is empty, nothing is going to come out of that. So then if this set here is empty, then there is not going to be a beta 1. I can't match anything. But to compute what goes into this cell, which cells do I need to combine? This one with, so 0 to 1. Which one? This one. So these two cells actually are adjacent. Because this one ends at 1, and this one starts at 1. So to be adjacent means that the end index of the first one is the start index of the second. We see that here. So I plus j, I plus j. So these two can combine, and together they go from 0 to 3. So the result of combining these two goes here. Is there another pair of cells that can combine for 0 to 3? Yes. Yes, so 0 to 2, this cell, if there were anything here, could combine with 2 to 3, this NP. And again, the result would be recorded here. So adjacent in terms of next to each other, in terms of the corresponding substrings, does not mean next to each other in the table. Does not necessarily mean that. Okay, so that's a relatively simple algorithm. I mean, the indices are fiddly. You need to get them right. But it's 3 nested loops, so that here I will compare, I'll fill in one diagonal at a time, and I'll compare all of the right pairs of cells. What can we observe about the complexity of this algorithm? How do we do rough complexity analysis? We did that for Viterbi, didn't we? Sure we did. Yes? The 3 nested for loops, yes. That's a, yes. You were, the initialization, we'll discard that. We take the largest. So you said there are 3 nested for loops, and then you took a jump. You said that makes it cubic. I think we also need to observe that each of the for loops iterates effectively in n, for n being the length of the input. So if we say length of input is n, then this for loop iterates n times, n plus 1 times, n times. Sorry, here, L. So the largest value that L can have will be n minus 1, in fact. So this for loop will iterate, the smallest value that L can have will be 1. So this will go to n minus 1. And the largest value that L can have will be n minus 1. So this will go to n minus 1. So broadly speaking, or roughly coarsely counting, all 3 for loops iterate n times, and that makes it cubic. So we have a cubic algorithm. It's not half shabby. Cubic is good. Cubic is okay. Polynomial is not as good as linear, but manageable. And it seems that we're solving the parsing problem, because we work out that this string actually is a sentence of the language. We determine that by observing that from 0 to 5 in the top right corner of the matrix of the chart, there is the start symbol. That means we have recognized we accept this string. Okay, let's reflect a little more about some built-in assumptions we're making that are not warranted from what we have said about context-free grammars so far. We assume, or the CKY algorithm assumes, a limited, simplified, restricted variant of context-free grammars. It's the variant known as Chomsky normal form grammars, where all of the rules have one of these 2 forms. Either it's alpha goes to beta 1, beta 2, where beta 1 and beta 2 or beta I is a non-terminal. It's no longer the union, it's just the just C, the non-terminals. Or there's a single terminal, gamma, on the right-hand side. Is that gamma? Yeah. So we are, if you compare that to our original statement about the form of the productions, this is much more rigid. We no longer say beta I, beta 1 to beta n, beta I element C union sigma. Now we say it's either exactly 2 categories or exactly 1 terminal, 1 word. So that's a subset of the context-free grammars. That's the subset we're assuming because, as you observed already, here in the initialization, we look up only by 1 word at a time. And we assume that words and non-terminals categories don't mix in right-hand side of rules. Furthermore, here we implicitly assume that it's sufficient to try to combine pairs of cells. That is, all the grouping we attempt will only ever be in terms of two things that we try to group into a new constituent. This, sometimes called source cell 1, and this source cell 2. Two cells from the matrix. So that's a formal constraint we put on the context-free grammars that the CKY algorithm can process. Yeah? You're already trying to generalize it? Or? But if you so the question is about how to generalize it to arbitrary context-free grammars, or at least grammars that go beyond Chomsky normal form. And essentially what you would have to do is some way of trying combinations of more than two cells at a time. So you would have more, you would need more loops in here. And there would have to be as many loops as is the highest number of right-hand side elements. And you would have to be more clever about the initialization and all of that. Yes, that would be possible. There are so-called generalized CKY variants, but we'll actually generalize even further and work over. So we are observing these to motivate us to do better. I mean, late 60s, Kasami younger, it's not that natural language processing has not made any progress since then. But the CKY algorithm was the first to take advantage of that key insight, the local ambiguity, and compute what we can interpret as a parse forest. So some assumptions we're making to just criticize, that's a common technique in teaching. We put something out, looks good, and then we turn around and criticize it to motivate something even better. So CKY is limited to CNF, Chomsky normal form grammars, and you can do a lot of syntax in Chomsky normal form, but theoretical linguists hate to be constrained. So they would say, well, give Sandy a book. That's obviously VP goes to V, NP, NP. You're going to say, I can't write that in my grammar? Then I don't want to talk to you. So a rule like VP goes to V, NP, NP seems very motivated. Or even, I bet Sandy $5 that it would rain. Sandy, $5, so there are even 3 elements in addition to the verb. And I couldn't write down rules that combine those, that group those into one constituent in CNF, in Chomsky normal form. Another built-in assumption is that the algorithm has a fixed order of computation. It's breadth first, it's exhaustive, in the sense that it always computes all values for each cell before it can move on. In this example, we're only ever seeing one category in each of the cells, or 0, but in principle, of course, there could be substrings that are ambiguous, that are category ambiguous, that have more than one category that they can derive. And I need all of these available for the shorter substrings before I can do something about the larger substrings. Because otherwise I would not be complete. And that sort of goes hand in hand with this rigid bottom-up control, bottom-up left to right control structure. It has to do one diagonal at a time. Often in natural language parsing, we're actually not interested in all the 4,000 different interpretations. I mean, a theoretical syntactician would be, I used to be one 20 years ago, a parser developer, what I've been doing since, and especially if you build parsers for practical applications, typically you want to know what's the most likely, what's the one analysis you think is the right one. Sometimes you want an n-best list, the 10 most likely analyses. But very rarely in actual applications do you want all of them. So this exhaustive, rigid control structure is not nice. It's not great. And so we'll move beyond that in a framework called generalized chart parsing, which takes the key inside local ambiguity factoring and is similar to CKY. There are edges and a chart, but it adds a few more pieces. that allow us to liberate the order of computation. Um, I can fill in the cells in any order is what that means and still be correct. It allows us to process arbitrary context-free grammars, move beyond Chomsky normal form. And it will do so by adding an additional type of edge, so-called active edges. And they, in the chart, in the table, represent partial rule instantiations. They represent, if you will, intermediate states of computation. So the basic process is always to try to find all of the right-hand side elements of a rule, and then say, I can group these. I introduce a new constituent. And here, I'll now introduce additional entries in the table, in the chart, that keep track of how far have I come in finding elements of the right-hand side. So we'll write these down in a notation like this, where we're processing a rule, say VP goes to VNP, at some position, 1 to 2, and the dot in the rule tells us how much of the right-hand side have we actually found already. At this point, we have found a verb. We have the expectation to find a VP if only we find an NP right next to the verb. So this is a partial state of computation, an intermediate state of computation. And adding these active edges is one of the two key additions to the CKY algorithm that gets us around all of these limitations. So I think I'll go through this slide. Oops, this slide. And maybe actually leave the... we're a little behind where I wanted to be today. So high level still. We're computing a chart, this kind of graph, indexed by substring positions. The same counting the interword vertices just in CKY. And we apply local ambiguity factoring, or packing as it's called, the key inside. We treat multiple ways of deriving the same category for some substring as equivalent. We'll only put one edge, one entry into this graph. As we did, that's where we started. So in a sense, all of this is, well, except for the partial analyses, depending on how you interpret that all applies to CKY too. And did I get my slides out of order here? No. This already gives us some benefits that maybe weren't so apparent when we talked about CKY. And it's a dynamic programming algorithm in the sense that the chart actually keeps track of parsings, constituents that I have found for subproblems, for shorter strings. Each substring is parsed only once. And whatever I can find for that substring is recorded in the table. And so when that substring occurs as a larger string that I'm parsing, I'm not repeatedly trying to parse the same substring over and over again. I have a very efficient indexing scheme because it's all keyed off the substrings, the counting of interword. Looking up in a table is very cheap. It's two indices, two numeric indices. And what I end up doing here, I think I'm a little unsure of the order of slides here currently. And what I end up doing here is I compute a parse forest in polynomial time, as the CKY algorithm did. But that parse forest, that graph, that table with the edges, actually is a description of a set of trees. And so in that respect, it has an exponential extension. I characterize, I describe, I capture, I determine an exponential set of trees in a data structure that I can compute in polynomial time. That's the squaring of the circle in a sense. Still, if I wanted to actually take out the individual trees, I would have to invest more effort. If I wanted to take out all trees, I'd be back to exponential. I think I actually have to stop here, so I'll keep you in suspense about how the active edges actually help us to generalize the CKY algorithm to what we'll call generalized chart parsing. The basic notions are in place at this point. Okay, then I'll see you next Thursday. Last lecture on natural language parsing.